Uh, Dr. Okay, today we have two speakers. The first speaker is Dr. Kamimura from University of Tokyo. Please.
Okay, thank you very much. First of all, I would like to thank the organizers for having me today. So today I want to share our recent work on chemical thermodynamics of growing system. And this work is in a collaboration with Yuki Sugiyama, Dimitri Luchko, and also Tetsuya J. Kobayashi, all in our group in the University of Tokyo. And today I'm going to talk about a work that is already published in these two papers. The one is Physical Review Research 2022, and the second one is more really recent one that we published this month, this May, about 1 or 10 days ago. So that will be the second part of this talk. Oops. So the topic is also, of course, autocatalysis. Autocatalysis is a very important property of living systems, and maybe many people have been asking many questions about autocatalysis and maybe what are the sufficient and necessary conditions, or what are the universal features, or how does an autocatalytic cycle appear, or how can one build autocatalytic systems. So there could be a many series of previous work, but if we consider autocatalysis in chemical reactions, so maybe the problem could be roughly categorized into two problems shown here. The first one is a network structure of chemical reactions. So maybe there could be many kinds of network structure of chemical reactions, and the question is, can all the members increase as reactions progress or not? And the second question is, or second problem is it's called thermodynamic constraint, that even though the network structure has a potential to increase all the members, but all the chemical reactions are physically reversible. So the problem is, do the reactions progress to increase the members? And for the first questions, so I want to start with a very simple example that I shown here. And so let me consider this is this very simple reaction. So here in the first reactions, B1 and A1 becomes 2A2. And in the second reactions, A2 becomes A1 and B2. And if we consider this kind of reactions, maybe most of you know that we can write a stoichiometric matrix that in this matrix, we label in line or in row, we assign each chemicals B1, B2, A1, A2, and in column we assign the reactions 1 and 2. And you see the element of this stoichiometric matrix is, for example, if reaction 1 progress, 1 B1 and 1 A1 is consumed and produce 2 A2. So the element of A2 for reaction 1 is 2. And similarly for reaction 2, you can write 1 A2 is consumed and 1 A1 and B2 are produced. And if we write this matrix S and O, so you can write the dynamics of B1 and A1, A2 and B1, B2 is a product of this stoichiometric matrix and the reaction flux JR. And this is a very general mathematical representation. But if we focus on this blue part, A1 and A2, so this matrix S has a 2 vector, -1, 2, and 1, -1. And if you write here in the right figure, if you write the change of A1 and A2, this green vector shows the vector -1 and 2, and this yellow vector shows this vector 1, -1. And you see that when these two vectors are linearly independent, you can make this kind of red vectors. This means that by some combination of reaction 1 and 2, you can make both of A1 and A2 increase, effectively increase. So this is a kind of, by this, so we can say that this reaction is autocatalytic for this blue part. And you can say that if this green vector and yellow vector are linearly independent, so that means this matrix S is regular. So if S is regular, you can make both of A1 and A2 to increase this A1, both of A1 and 2 by this reaction. And maybe most of you know that recently one of the organizers published a very beautiful result in PNAS that if you consider a regular stoichiometric matrix S, you can mathematically prove that all the members can increase by reactions. And they call that minimum motif as an autocatalytic cores. And for example, for these reactions, you can graphically represent A1 becomes A2 and A2 becomes A1. And maybe most of you know that for regular S, they categorize the network structure into one of these type from type 1 to type 5. And for example, some realistic reactions can be categorized into one of these 5 types. But the problem I want to address in this talk is a second question that I mentioned in the beginning. So that is a thermodynamic constraint. And as I said, all chemical reactions are reversible, so that it's not always the case that the reaction could progress in the direction to increase the members. And for example, in this simple example that I just talked, for example, in the left figure, if the green vector is pointed like this and the yellow vector pointed like this, then you can make a red vector like this so that both A1 and A2 increases. But in other case, if green vector points like this and the yellow vector points like this, the red vector points like this, so that as a result, A1 and A2 decreases. So that means we could not produce both of A1 and A2. And that is the question that I want to talk in this talk. And maybe, so we are going to talk about thermodynamics of chemical reaction system. And maybe in thermodynamics, one very important state is known that is a chemical equilibrium state. And what is chemical equilibrium state? That is a state such that the chemical potentials of reactants and products are balanced. And that is somehow definition of chemical equilibrium state. And if let's consider this simple reaction, simple examples. And if we write the chemical potential of A as a yi, and if you write the chemical potential of B as a mu m, then you can write that the chemical potential of reactant mu1 plus y1 is balanced with 2y2, and in the second reaction, y2 is equal to y1 and mu2. So this is a definition of chemical equilibrium state. And if you write using the matrix S and O, so these equations can be written in a general form that ys plus mu O equals 0. And we consider the case when S is regular, so that these equations can be always solved, and the solution YEQ is equal to minus mu M or mu more times the inverse matrix of S. So that when S is regular, we can say that the chemical equilibrium state is uniquely determined given mu m. And the thermodynamics tells us that under given constraint, the system approaches this state, the chemical equilibrium state. And even though there could be many constraints, or we can consider many constraints, but in this talk, I want to consider a constraint when the chemical reaction system has a hierarchy or hierarchical structures. And you know that the cell or more simpler system, protocell, has a kind of chemical reaction system that the chemical reactions occur in a finite volume, and also the volume also change in conjunction with the reactions inside. And that kind of constraint that we want to mention, and why the role of volume change is important, because, for example, chemical potential or reaction flux is a function of density or concentrations. But actually, by the chemical reactions, the number of chemicals change. So that when the chemical reaction occurs, the number change, so that the density could change. But if the number change, the volume also could change, so that the density and also chemical potential could change. And this triangle, number, density, and chemical potential, could be consistently changed by the chemical reaction. And that's the, how to say, the constraint that I want to mention in this study. And under such variable volume, we recently developed a chemical thermodynamics of autocatalysis, and the first work was published in 2022, and that I want to introduce an outline of this work. And to formulate the problem, we generally consider this kind of system or setup. And here we consider a system that actually the chemical reactions occur. And this system is attached to the big environment, this green part, with a temperature T tilde and pressure pi tilde. And here we consider two kinds of chemicals, the blue one and red one. And blue one is we call the confined chemicals. And so the confined chemicals are very confined within this system. On the other hand, these red particles or red chemicals we call open chemicals, so that open chemicals go in and outside very freely between this boundary. And we consider that the chemical potentials of these open chemicals in the environment as a mu tilde. And we generally consider that inside this system, some reaction occurring S plus times AI plus O plus BM becomes S minus AI plus O minus BM. And the dynamics of this, for example, confined chemicals AI, the number of, if we denote the number of AI as a xi, so dx by dt is as I mentioned, that the change is written as a product of S, the stoichiometric matrix, times the reaction flux JR. And similarly for open chemicals, the number of BM we denote NM is denoted by the change by the chemical reaction, that is the stoichiometric matrix O times JR plus diffusion flux J. And here of course, we can consider many different kinds of assumptions, but here we consider very importantly, make a pretty important assumption that the first one is S is, of course, regular or fully ranked. This matrix is a regular. And the second one is, of course, the chemical reactions occur inside system, and also energy is exchanged between system and environment, and also diffusion occurs for these open chemicals. and also the volume could change, but we consider that the time scale of this reaction is very slow, so that given xi, this energy between system and environment is rapidly relaxed to its equilibrium state, and also that for red particles, the chemical potentials inside the system and the environment is rapidly relaxed to its equilibrium state. And also the volume is rapidly relaxed to the equilibrium state given xi. So that is the second assumption that we make for simplicity. And the third one is we neglect the dynamics of membrane or division or phase transitions. That maybe we want to start from the very simplest setup so that we neglect the dynamics of membrane division and phase transition. And under these assumptions, there are two very essential constraints in this system. The first one is that I mentioned in the first part. It is a chemical equilibrium state. So that is a balanced chemical potentials. So that the chemical potentials of confined chemicals, this blue one, is for regular S, you can write YEQ is uniquely determined by minus mu m O S inverse. On the other hand, as I said, the chemical reaction is very slow, so that the system is, for example, pressure of the system and the environment are always balanced. So that and if you consider the ground potential density of the system, and that we denote by phi star, y is a function, y is a chemical potential of confined chemicals, so that thermodynamically we can say that the pressure of the system is given by phi star y, and the pressure of the environment is given by pi tilde, so that these two quantities are always balanced. So that is another constraint for the system that we are considering. And given this constraint, the volume omega of the system is given by generally in a variational form like this. And so this is a very general form. Yes?
Excuse me, what is X and what is Y, just to be sure?
X is a density of confined chemicals. So X is a xi, and Y is a chemical potential of the confined chemicals. So X and Y is a vector and has an index I.
Yes. Okay.
Okay. And of course, we generally write the ground potential density as a phi star. But if we consider an ideal gas, this form is reduced to a conventional PV equals nRT, or maybe it's an ideal gas, so that the VV volume could be obtained by the number of chemicals, temperature, and pressure of the system. And given this constraint, we can write the total entropy, total of system and environment, entropy of system and environment could be written in this form. And here is a volume of the system times some terms that we call Ky. And Ky is composed of phi star YEQ minus pi tilde minus some distant measure between YEQ and the present chemical potential Y. And dy is called the Bregman divergence, which is generally defined like this. And also YEQ is a uniquely determined chemical equilibrium state. And given this entropy function, we can predict that the fate of the system, whether the system grows or shrink or goes to equilibrium. And we find that the condition when this difference between phi star y eq minus pi tilde is positive, the system grows. And when these two values are equal, it goes to the equilibrium state. And when this is negative, the system shrinks. And we note that we assume that the S is regular, so that the regular S results in the absence of non-equilibrium steady state. So that the system always grow, shrink, or go to equilibrium state. And of course, using these simple reactions, we can numerically show that when these three conditions satisfied, for example, red one, the volume increase so that it grows, or when the blue one goes to equilibrium state, and also the green one, it goes to shrink and finally vanishes. And when first we consider when the system can go to equilibrium state, that means this pi star y q minus pi tilde equals 0. So if we if we consider some chemical potential space, so this is a case for this simple example, so that we have two-dimensional chemical potential space, y1 and y2. And there's a unique point YEQ, which is defined as this one. And also, as I said, there's a two constraint YEQ and also the isobaric condition. That means the phi star y is always equal to pi tilde. So the pressure of the environment and system is always balanced. And so in that case, the system is constrained in this curve, IY, that we call IY. And you can say that when phi star YEQ minus pi tilde is 0, this YEQ is on this IY. So that when the system starts from one of this point, it goes to this point so that the system can go to equilibrium state. But when the system cannot go to equilibrium state, for example, when this value is positive, so this IY is located like this, but the YEQ is located here, so that the system is constrained on this curve, so that even though from some initial conditions, it cannot go to this point, so that the system cannot go to equilibrium state. And on the right side, when it's negative, IY is located like this, and YEQ is located here, so that in this case, it's also the system cannot go to YEQ. So that in this both case, the system cannot go to equilibrium state. But what makes the system grow or shrink is a sign of this Ky, the somehow coefficient of the entropy function. And as we found that when this difference is positive, on this IY, there's some area that the Ky is positive. So in this case, it's a case that there's some area that we call Ry, and on this point, in this region, the Ky is positive on this IY. And on the other hand, when this difference phi star YQ minus pi tilde is negative, the value of Ky is always negative on this IY, isobaric condition curve. And what is difference? Because if you write the entropy function as a function of the number of the chemicals, xy and x2, x1 and x2, then you can, so the landscape of the entropy function looks like this. And as I said, when the Ky is positive, so in the number space, it correspondingly, on this ray, in this area, the entropy function increases as xy or x2 increases. On the other hand, in the right figure, when this phi star YQ minus pi tilde is negative, always that on any ray, the entropy function is negative or increases as the system goes to the origin x equals 0. So that the second law of thermodynamics thermodynamics tells us that the entropy should increase so that when in the left case, it go from some initial condition, it goes to the infinity, so that the fate of the system is that the system will grow. And on the other hand, in the right case, the entropy increases as it approaches the origin, so that the system will shrink and finally vanishes. And this is the first part. 5 minutes, okay. So this is for regular S, but recently I extend to a bit non-regular, to the case non-regular S, and non-regular but not so general, but we consider that when the kernel dimension of kernel S transpose is not equals to 0, but still dimension of kernel S is equal to 0. And in that case, there's a vector U such that US equals 0. And from this dynamics, you can say that if we multiply U from left, you can say that in this system, there's a conserved quantity, or there's a conservation law. And so this L, or U times X, is conserved and given by the initial condition X0. And in this case, we show that the fate of the system changes, and essential is that when, if the case changes when L equals to 0 or L is not equals to 0. And if you say conservation law, you know, some people think that it's a mass-like conservation law, but in the mass-like conservation case, the component of U is non-negative. And in that case, you know, the change is constrained in this plane so that both of E or ER or both chemicals could not increases. But here we consider autocatalytic or conservation law such that U has a both positive or negative component, positive and negative components. So in this case, the system is constrained like this, so that still the system, the number of X1 and X3 can increases, so that even though there is a conservation law, we can consider that the autocatalytic system. And in this case, you know, for regular S, as I said, YEQ is uniquely determined. But when S has a left kernel space, you know, this equation, the solution Y is not unique, but there could be a many Y. But if we define Y mean to give a minimum phi star Y, then using this Y mean, we can say the fate of the system could be categorized in like shown here. And when L equals 0, so conserved quantity is equals to 0, the fate is similar to the case of regular S. So when this one is positive, system grows. But when L is not equals to 0, the fate changes so that when this difference is positive or equals 0, the system grows. And when this one is negative, the system goes to equilibrium state. And actually, for example, using this kind of simple reaction, we can numerically check that for phi star Y, there's a minimum Y mean here. And given this phi star Y mean, if Y mean is phi tilde is equal to Y mean, the L, when initial condition satisfied L equals 0, it goes to equilibrium. But still, if it's not non-zero, it still grows. And when phi tilde is smaller than that, in any case, the system grows. But on the other hand, when phi tilde is larger than phi star Y mean, the L equals a shrink, but for non-zero L, it goes to equilibrium state. And actually, I could not tell the details, but in this case, isobaric condition that we consider in the first case, but when conservation law exists, the system cannot go access to all these isobaric conditions, but because of the conserved quantity, for example, depending on L, this isobaric condition is partitioned into some parts of the area. And one can say that and also chemical equilibrium state is not unique, but there could be a many chemical equilibrium state like shown by this red curve. So we consider that the isobaric conditions of this gray simplex and curve of this red one, then when this condition is satisfied, there is no intersecting point between this red curve and gray simplex. So that means the system cannot converge to equilibrium state. But when this condition is satisfied, there is a one unique intersecting point between this red curve and gray isobaric condition, and we can show that this point is always on the stoichiometric compatibility class for L equals 0, so that when L equals 0, system can go to equilibrium state, but still for non-zero L, it grows. But when this pi tilde is less than pi star y min, in this case, there's an intersecting point for non-zero L, so that the system can go to equilibrium state for non-zero L. But in this right case, there is no intersecting point between this L equals 0 STO and this red curve, so that for L equals 0 case, the system cannot go to equilibrium state, and in this case, system shrink. And sorry, so actually, if the system grow or shrink could be predicted by the shape of the entropy function, but actually, in the left case, the entropy increases as the volume or the number of chemicals increases, so that in this case, the system grow. And in the right case, L equals 0, the top of the entropy is located in the origin, so that finally the system shrink and finally vanishes when the L equals 0. So I'm sorry, time is up. So I want to summarize my talk. So recently we developed a chemical thermodynamics of growing system, and in the first part, we consider regular S, and we formulated environmental conditions for systems growth, and also identify the constraint on the steady growing state. And the first part is published 2 years ago, 2022. And recently, we extend this regular S to a case when S has a left kernel space, and in this case, the fate also depends on the initial conditions. And this work is recently published in Physical Review Research. And so, as a perspective or a future work, there could be many extensions of our framework. For example, if we include membrane dynamics, or mixed time scale of chemical reactions and diffusion, and also important future work is when we consider right kernel space and also phase preparation or division. So thank you for your attention.
Thank you.
Thank you.
Because